Hello everyone, good day. Today we will do some questions and answers of interior of the earth. Most of the questions are taken from NCERT. I would encourage you to pause the video and try to think and come up with answers on your own. So let's begin. Question is, how are the convectional current in the mantle initiated and maintained? We can write it in one line also, saying radioactive decay causing thermal difference in the mantle, thermal difference or temperature difference in the mantle initiates and maintains the convectional current. Okay, now let's explain it. Suppose you have kept a tumbler full of water on a furnace which is heating it from below. The water which gets heated first will become lighter and move up. Similarly, the cooler water will subside, forming a current. This is what we call convectional current. So similarly, Earth's mantle is also heated, and as I told you, it is due to the radioactive decay. What is radioactive decay? There are some elements in Earth's mantle, such as uranium, thorium, potassium. Some of their isotopes have unstable nuclei, which breaks down into nuclei of some other element and releases alpha, beta, or gamma particles, and also releases lots of energy. This process is known as radioactivity, due to which a lot of heat is produced, and hence in mantle also we find that the heated part of the mantle moves up and the cooler part comes down. So is radioactivity the only source of heat in mantle? So mostly yes, but then there is another source also, which is formation of the earth. When earth was formed out of hot gases and dust which accreted together. So since it was already hot, and then when it came together due to the gravitational force, the collision between the particles produced heat. So that's why interior of the earth is hot. So the primary reason is radioactive decay, and the other reason is formation of earth. And due to these things, mantle gets heated, the heated part of the mantle moves up, the cooler part subsides, and hence forming a convectional current. As long as this heat will be there due to radioactive decay, this convectional current will continue to be produced. Let's move to the next question. The question on our screen is, briefly explain the indirect source of information of the interior of the Earth other than those of seismic activities. There are two sources, direct and indirect, of understanding the interior of the Earth. To avoid confusion, just remember what are the direct sources. The direct sources are drilling inside the Earth, but since you cannot drill, we haven't been able to drill beyond 12 kilometers. So the second direct source is volcanic eruption. Volcanoes erupt and they bring out magma onto the surface, and we get to know what is the interior of the earth composed of. We have to write about indirect sources. Let me list it first. There are three main indirect sources. First is meteorites, second is magnetic surveys, and third is gravitational force of the earth. let's explain the first. During the early universe, it was composed of dust and gases which was moving fast. But due to the gravitational force, it started to come together, and due to this accretion, they formed sun, that is the star, planets, and other celestial objects. Sometimes meteors enter into the Earth. Most of it gets burnt and exhausted due to the friction it experiences because of the Earth's atmosphere. But the larger ones are able to reach the interior of the Earth. Their outer surface gets exhausted of the meteor, but their core remains intact. And we find that their cores are made of nickel, iron, and other heavy elements. That's why we can infer from this that Earth's core must have been formed by these elements, because the formation of Earth, other planets, or meteors is similar in process as well in the materials involved. Second is magnetic surveys. When we do a magnetic survey, we use magnetometers, and we try to find out the strength of the Earth, magnetometer, sorry, and we try to find out about the strength of the Earth's magnetic field in different part of the Earth's surface. Different materials affect this magnetic force differently, and that's why we find that the force of magnetic attraction, magnetic force is different in different surfaces, and hence we can find out that the underlying rocks must be made of different kind of material. So we can infer that what kind of material is present inside of the Earth's surface, and which is causing this difference in the magnetic force. Hence, we can say through this we are only able to tell about the distribution of different element or materials, let's say, in the Earth's crust. Also, the fact that Earth has a magnetic field around it tells us about what is going on inside the Earth's core and the materials with which it is composed of. A third point is gravitational force. You see, gravitational force of the Earth is different in different parts of the Earth because it depends on mass, and mass depends on, density is mass by volume. So mass depends on density and volume. Suppose density of some rocks are different than the other. So even if they are big, the gravitational force of attraction caused by it would be lesser. Thus, because of the, we call the difference in gravitational force, which we expect a landform to exert, than its actual gravitational force as an anomaly. So gravitational anomaly tells us about the material of which a landform is composed, or the interior of the landform is composed of. That's why we say that this is an indirect source of understanding the interiors of the Earth. I hope you have understood it. If you have any doubt, you can write in the comment section. The location of the Indian landmass during the formation of the Deccan Tribes. If you know the answer, you can pause and write it on your own. You know that Earth's crust is not static. It is formed out of lithospheric plates and it floats over the molten asthenosphere and hence keep moving from one place and position to another. You know the continental drift theory. There was a supercontinent called Pangaea, broke into two parts, Laurasia and Gondwana. India was in the Gondwana part. The southern one was Gondwana. And then about 200 million years ago, India started to move uh, from south and then collided with the Eurasian plate. Okay. So question is asking us about the Deccan Traps. So Deccan Traps were formed during the Cretaceous period, which was 60 million years ago. So where was India during the Cretaceous? India was in the southern Indian Ocean, south of the equator. That is the present southern Indian Ocean, just above the Reunion hotspot. And magma erupted out of the Reunion hotspot, forming the Deccan Traps and the Deccan Plateau. And then India moved towards north, where it is right now. Similarly, there were other hotspots also. Tristan hotspot produced this Parana plateau. So along with these extrusive landform, we also find that it leaves a tail, volcanic landform tail, because as India moved out of the Reunion hotspot, it continued to erupt volcanic materials, and hence we find that these kind of volcanic landforms are there forming a tail. Next question. What were the major post-trip discoveries that rejuvenated the interest of the scientists in the study of distribution of oceans and continents? Wegener was the proponent of continental drift theory. He proposed his theory in the early 1920s, but then he died in 1930. Till his death, there was very little recognition of his theory because he could not give the reason, the force behind the movement of continents to such a vast scale. He said that there are two forces. One is the tidal force, which is the gravitational force of the sun and moon, and the other force is rotation of the earth. But since these were ineffective, this theory did not get large recognition. But then there were several post-trip discoveries which rejuvenated the interest of the scientific community. The first one we can say was convectional current theory, which was given by Holmes, Arthur Holmes in 1930s. So Arthur Holmes was trying to solve this problem of the force why continents might be moving. So he said in the mantle there are convectional current, as I told you, because of the radioactive decay of the elements. There is thermal difference in the mantle because of which the hotter mantle is moving up, colder mantle is coming down, producing a convectional current. And he said that this could be the force which is moving the plates. If there is a plate and then there is a convectional current beneath it, then we can say that this might produce some force, how this plate is moving. Then the other studies were mapping of the seafloor. Through through mapping of the seafloor, we found that the seafloor or the oceanic crust is not monotonous, but it has very interesting features such as trenches were present along the continental margins, and there were sea ridges in the mid-oceanic basins. The presence of these sea ridges was the most important factor which helped us in the confirmation of the continental drift. So before we explain the sea ridge phenomena, let's also tell you that when we try to find out the age of the oceanic floor, it was found that none of the oceanic crust was more than 200 million years old. While you know that continental crust has been found to be more than 3 billion years old. So oceanic crust is quite newer as compared to the continental crust. So either 200 million years old or even less. So in the we found that there was a belted pattern of belted pattern of volcanic eruption, and there was a series of volcanoes along these mid-oceanic ridges. These volcanoes erupt magma, then it gets solidified and formed this newer oceanic crust. We found that suppose this, let's say this is A, this is B, this is C. So age of oceanic crust A is newer than B and B is much newer than C. So C is older, B is less older than C, then A is the most newer. So we found that newer oceanic crust is being formed at the sea ridge and it is being pushed away from the ridge, and we found a symmetry in both the sides. And this symmetry is not only in terms of age. When we try to find out the polarity, the magnetic polarity of the rocks. So before explaining that, let me tell you that from time to time the polarity of the Earth's magnetic poles changes. And when a molten material gets solidified, so the polarity of that time when it is getting solidified is frozen inside the minerals of the rock. Suppose it's a magnetite rock, it is in molten form. So when a material uh, reaches above its Curie temperature, it loses its magnetic properties. So if it is molten, then of course it is above its Curie temperature and it has lost its magnetic properties. Now, when it comes on the surface, it solidifies, the magma solidifies, and according to the polarity of that time, suppose it is Cretaceous and Earth has a different magnetic polarity than today, then it will solidify. The minerals will show the magnetic polarity of that time. So A on both sides had a similar magnetic polarity. B had similar magnetic polarity. C had same magnetic polarity. So the rocks equidistant from the from the oceanic ridge had similar age and similar magnetic polarity. This proved that oceanic floor is newer oceanic floor is being produced on the sea ridge and it is being continually pushed away. This theory was collectively known as seafloor spreading. The next important discovery was polar wandering theory or polar wandering curves. So this is a continent, and in this continent there are rocks of different ages and which have been produced when magma got solidified in it. Suppose this is of Cambrian age, this is of Triassic, this is of Cretaceous, and so on. All of these rocks show magnetic polarity in a different direction. So it shows that magnetic pole would be here in Cambrian. This is showing that magnetic pole should be in this direction. Let's say here. This is showing that magnetic pole should be in this direction. So We on a globe we join these magnetic poles of different ages and form a magnetic apparent magnetic pole wandering curve. So two of the possibility can be thought of. One, the magnetic poles have actually moved from this to this place in this manner, or the magnetic poles have roughly remained in somewhere in the same position, but the continents have moved over time. So the second proposition is more probable. So this is showing that continents have moved over time. Similarly, when we draw a magnetic curve of a different continent through same method, we find that it has a somewhere different magnetic curve, say like this. So the difference in apparent wandering magnetic poles so that continents have also moved relative to each other. So this also corroborates the continental drift theory. So together all these theories, seafloor spreading, polar wandering theory, convectional current. So collectively all these led to the proposal of plate tectonic theory. Similarly, we can explain that why and how plate tectonic is a major improvement over the continental drift theory.